Okay, number 343, a kinematics problem, and it's got some context. The person on a bungee cord has just jumped and their height is given by this thing. Okay, so obviously when you do a bungee jump, I imagine you're already elevated, and you can sort of see that if you put 0 in here for t, and you get your starting elevation is 100 meters above base, whatever the ground level is, shall we say. And that describes a cubic relationship. So the bungee, you're starting up high, etc., and obviously time along here, tick, 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 as you go along. So the key thing here is we're going to find the minimum, maxima, and pretty typical kinematics, sorry. H, differentiate that. You're going to get velocity, differentiate that again. You're going to get acceleration. So differentiate with respect to time gives you velocity. And a lot of these kinematic things, especially with displacement, is the minimum and the maximum occurs when the velocity is 0. In other words, put v of t equal to 0, find t values, and these t values, in this case, I imagine one's going to be a minimum, one's going to be a maximum. Hey, what we're just going to do here is have a wee pause, and let's sort of cheat in a way. Let's go to Desmos and see what the thing looks like. In fact, Desmos is going to tell you the answers. Yay for Desmos. So let's go up here. There's Des. And the formula was 100 minus x cubed. Obviously, Desmos works in terms of the variable x instead of t. Plus 15x squared minus 60t. Not t, sorry, x. Okay, and here's the problem. You can't see anything. So what you have to do, there we have it, up there. Okay, and this is pretty awful on the right here. So what I'm going to do is just go into here and double click this. Control A, select it. I'm going to say minus 10. Okay, and let's put here, Control A, 10 as well. And then I can shift it. So there's your cubic, and obviously, as we can sort of see here, 100 there. Hey, so basically straight away, there's one answer there, and there's one answer there. Go figure. Now, you could have done that with your graphing calculator, but the fiddly thing with the graphing calculator is reconfiguring the screen to sort of show you this sort of size here. But you know, looking at the formula, you get a feel for it. Hey, look, you know, time equals 0. It's going to go up as high as 100. So you have to arrange the y-axis, the y component of your screen to be at least 100 there. Righty. So let's go back to which way? This is the wrong way. Excuse me. New computer at home. Here we go. Okay, so let's differentiate this. So we're going to say velocity with respect to t is dh by dt, and that's going to be minus 3t squared plus 30t minus 60. So, because we've differentiated that expression there. Okay, let's put that equal to 0, and let's go to the graphing calculator, and it just so happens I've already pre-programmed it. So I've plugged in here menu, I've gone to equation. One of the options was solve polynomials, second order, because the highest power of x is squared. So the a coefficient, you can sort of see the coding at the top there, -3, the b coefficient 30, and the c coefficient -6. And it has to assume to put equal to 0. You can see that there. Push solve, and I get two solutions. Let's round these to, let's round them to 2 decimal places. So t equals 2.7, I think that's a 6, and 7.24 2dp. Okay, so the key thing here, as mentioned, to find the maximum minima, you've got to put this second order derivative, or the velocity statement here, because we're talking kinematics, and we found these points here. Now, which one is it, the maximum minima? Obviously, if you've got the graphing thing in front of you, not be surprised. There is your minima. It occurs at 2.76, and the maxima here, as predicted, 2.34. So algebraically, how do we show that? We've got to do the second order derivative. That's what I should have said before. So a of t is dv by dt, and differentiate that as minus 6t plus 30. So if we were to put in a of 2.76, okay, just looking at it, negative 6 times, call that 3 basically, and the value is going to be positive. So if the second order derivative gives you a positive value, you can say, therefore, at t equals 2.76 is a minima. Okay, and to confirm the other one, if we put in 7.24, okay, what happens? That's going to be negative 40 odd. So that's going to be negative. Therefore, at t equal 7.24 is a max point. Now, it did say find the minimum. So, whoops, we haven't quite done that yet. How would you find the minimum? You have to go right back to the original expression here and plug in h equals 100 minus t cubed. Well, okay, let's put the minima. So it's going to be, now it's minus 2.76 cubed plus 30 times 2.76 squared minus 60 times 2.76. Okay, and honestly, that looks horrendous. I think what that's just compelling me to do here is, yeah, let's be honest. Let's use this thing to its capacity. So let's go to graph, and we should have done this to start with instead of using Desmos. Obviously, with Desmos, hey look, there's the answer right there. If you plug in 2.76 into here, out pops 27.6. If you plug in that coordinate point there, out pops that. Just a fancy thing, if you want to call this a function, f of x, okay, see what I've just done there? I've called it a function, and if you want to get fancy, you could do this. You could say f and put in the value, what was it, 2.76, and guess what? It's telling you what it should be. Now, is that precise bit of rounding error there probably kicking in? But anyway, let's go back to using the awesome Casio. Okay, so the graph function here looks like there's some rubbish going on in here, so I'm going to have to delete, so a bit of prep here. Yes, delete, yes. And okay, this is, okay, so this is where the program comes a bit. 100 minus x power 3 plus 15 x squared minus 60x. And if we push graph, we're not going to see anything. That's the problem with this. So shift window setup. Oh, it's still thinking. There you go. You can sort of see in the top hand corner there. Just being a bit impatient. Okay, I'm going to have to say, let's go neg 5, maximum, I think 10 seconds. The scale is fine. The minimum, neg 5, and let's go 110. Scale 10, and draw. It's thinking on the corner there. The latest generation is a lot faster, and there it is. Okay, so now this is the cool bit. Shift G solve and go to maximum, and it's going to find that point up there. Okay, really having to chug through this. You can see that black dot there, that's telling the calculator's thinking. Whee, it's taking a while. And is that a fail from the calculator? Oh, that was interesting. Oh no, got there. Wow. Okay, so, and there, as you can see on the screen, is your answer, 72.36. Righty, that was a lot of work really, but we have just proved that, and obviously less than 8 seconds because a cubic will start to, well, that's when it gets sensible. The equation predicts that after 8 seconds they will continue on until they hit the water at h equals 0. What is the acceleration and velocity at the point where they hit the water? Great question. Okay, so basically what we're doing here is, there is the answer there, it's 10 seconds. Wow, the graph just told that straight away on Desmos. What about on here? If I did Shift G solve, no, wrong one, exit, draw, oops, shouldn't have done that. Anyway, here it comes. Okay, just got on Shift G solve. Obviously this is called a root, so we're going to say a root, and it's thinking. You see it thinking in the corner here. Let's just go on to show it's thinking. Okay, it is struggling to get it, so let's just do it the algebra way. The algebra way says, going back to here, the question says when h equals 0, after 8 seconds, so we know the time is going to be after 8 seconds. In fact, Desmos told it was 10, so we're going to basically put this thing equal to 0. Equal to 0, and yeah, and that's actually quite tricky. So, oh, by the way, it got there in the end. So, x10, and the value there is 0. So, if we were to do this using the graphic, the algebra approach in this, so let's do polynomials. This time it's going to be 3 because it's a cubic up here. So, actually, that is a mistake. We want 2. So what's the degree? 3, and we're going to say minus 1, 15, minus 60, and 100. And then we're going to solve, and it's giving us 2 complex solutions. If you did complex numbers, you'd realize why they're complex, but there it is, the real solution, x equals 10. Boom. Okay, so going back to here, so we've discovered that for part B here, and we have to now work out the acceleration. So, hello, we need to differentiate in an expression for acceleration. Acceleration with respect to time is dv by dt, and there it is there, negative 6t plus 30. So if we plug in here 10, it is negative 60 plus 30, and the deceleration at that point is negative 30. So they're pulling 3 G's when you hit the ground. Hopefully that's not going to happen in the actual thing. So let's just confirm we've got some correct answers here. Let's go to 343. Okay. Yep, we got those times, we got those heights, and we're seeing 10 seconds. This is interesting. Did the question ask us to... Oh, classic. I have not fully answered the question. The answer is what is the acceleration and velocity? We got the acceleration at -30, and I did put some nice units in here. And okay, just going back to velocity vector, if you plug in here 10, you're looking at, what's that, -300. What's that, plus 300. And so the answer is going to be -60. Okay, and obviously that's shown right there. The units are meters per second. Okay, so there is again quite a tricky one involving kinematics. Cool. Wrong way.